Thanks everybody for coming out tonight. This is great. I didn't know quite what to expect, but it's nice to see so many of you here. One correction though, I'm not actually a professor. I do have my PhD from the University of Colorado, but I work for the National Snow and Ice Data Center, and we are affiliated with the university, but we are actually a NASA-funded data archive center. So we are a location where all data that's collected relative to snow and ice, we store, we archive, and distribute it to the general public, as well as other scientists. So that's basically what we do, and we are unique as a data center of NASA in that we have several scientists that do independent research as well at the NSIDC. And I've been working in the Arctic for about, I would say, almost 20 years now. I was finishing my master's in aerospace engineering at CU and was taking this nonlinear fluid dynamics class that was quite difficult in the physics department. And a friend of mine was taking this climatology class in geography, and he was telling me how wonderful this class was, and I thought, that sounds like fun. I'm going to drop this really difficult class, and I'm going to take this climatology class. And the professor was really great, and he's actually the director of CERES, which is part of who we fall under, which is the Cooperative Institute for Research in Environmental Sciences. But he did a lot of field work in the Arctic, and when I saw the pictures from Greenland, and I saw the pictures of, sea ice and icebergs, I thought, I want to go there. So I basically switched over from engineering to geography to do my PhD, and my friend also did the same thing, and he's now the chief scientist at NASA. So I think it was a good move on both of our parts. I think we enjoy our work quite a bit now. So I'm going to talk about some of the work I've been doing, and I should preface this that what I'm talking about mostly is the last 30 or 40 years of climate change going on in the Arctic, because I primarily work with satellite data. So most of these observations are coming from the 70s to the present day. I don't work with paleoclimate data, so I'm not looking at trying to reconstruct what the past climate was like. I'm really just focused on what is happening today and trying to understand these changes that are happening today. So first off, why the Arctic? Well, for a long time, scientists and climate models have been predicting that if we're going to see some changes, some climate change, we're probably going to see it first in places like the Arctic. And the reason for this is that most of the Arctic, the same with the Antarctic, is covered by snow and ice for most of the year. And since it's covered by snow and ice, it reflects most of the solar energy that comes in from the sun during the sunlit periods back out to space. It helps to keep our planet cool. And so if the planet were to warm, you start melting back that snow and ice, you start exposing the darker surfaces beneath it, so the land or the ocean, which then absorb more of the sun's energy, and that causes a further warming and feedback effect, melting more of the snow and ice, and so on and so on. And so these are regions that are very sensitive to changes in temperature, and these are regions that are therefore quite important to monitor. And if you think about our planet, for example, because the poles are so cold, and because the tropics are so warm, all of our weather patterns, our atmospheric circulation, our oceanic circulation, are all driven by that temperature gradient between the poles and the equator. So if you start changing that temperature in the polar regions, you start warming it up, you're going to change your circulation patterns in the atmosphere and the ocean, and it's going to affect the weather worldwide. So this is one of the things that makes this an important place for us to start monitoring. This is a projection of global mean temperatures out by 2100 from some climate models that were used in a report back in 2007 from the IPCC. And this basically shows you that if we keep doing everything that we've been doing, just business as usual, that we can expect the Earth to warm by about 3 degrees Celsius by the end of the century. But if you look at the Arctic region, so if you go up north and you go to these regions, the temperature increases up there are much, much higher. They're about 7 degrees Celsius or about 12 degrees Fahrenheit by the end of the century. And this is based on that positive feedback effect that I mentioned, that if you take away the snow and ice cover, you're going to start warming that region up quite a bit. And so this is, what the projections are showing. And this is actually kind of outdated because we realized that the emission scenarios used in these climate models that were done back in the mid-2000s are kind of out of date in terms of our emission scenarios. We've already surpassed some of this. But this is sort of, a future projection of what temperatures are going to be looking like if we keep going as we have been going. So if we look at the Arctic and we focus first here in Greenland, which is where I first did my first field work as a graduate student. This is just, on the left here is as a melting day anomaly. So just the red areas basically indicate that you're melting more than normal. This was for year 2007 relative to a longer term average, which was starting back in the late 1970s to 2007. This is kind of showing the same sort of thing, but over time, just the area extent of the regions of Greenland that are melting, just over time from 1978 through 2010. And you can see that there's an increase in the area of Greenland that's been melting. And the thing that we've been noticing is that these higher elevation regions, so along the coast, it pretty much always melts every summer. But up here at summit, this is about 3,000 meters thick, doesn't tend to melt. So this is also about 2,000 or so meters thick. But you're starting to see these encroaching onto these higher elevation regions where typically it never really melted. And that's what this trend map is also showing, is that the total melt extent is increasing over time. But if you look at these ones that are just above 2,000 meters, which is this dotted line up here, you're seeing that you're also starting to melt further up the ice sheet. Besides that we're melting more of the ice sheet, we've also been noticing changes in the glaciers that are flowing off the Greenland ice sheet. So when you look at Greenland, you have many of these outlet glaciers. This is the Jakobshavn Glacier, which is the place that I went when I was first in Greenland. And these are just examples of where the grounding line used to be. So this is 1851, going all the way back to 2006. So you see this big retreat here in the grounding line of the Jakobshavn Glacier over time. What is concerning about a lot of this is that what scientists are now discovering is that the mass loss from Greenland, it seems to be equally split now between melting and runoff, and also icebergs that are calving off of these glaciers. So a lot of the glaciers in Greenland have been accelerating in recent years, dumping a lot more of their ice into the ocean. And this is, when we talk about sea level rise, what you're really concerned about is places like Greenland and Antarctica, because Greenland, for example, contains enough fresh water that if you were to melt the entire ice sheet, you would raise global sea level by about 24 feet. So, and typically, we thought that these regions were very slow to respond. We didn't think, even in some of these projections of sea level rise in the future, we weren't really considering Greenland to be that responsive yet to warming temperatures. But in the last few years, it looks like Greenland has been, really accelerating its melt, and part of that has been also these changes in the discharge rates of these glaciers. And part of the processes that scientists have been looking at is that as you're having more surface melt, when that meltwater drains through the ice sheet, it can lubricate the bed of the ice sheet, causing some of these glaciers to speed up and drop more of their icebergs into the ocean. It's still a little unclear, I would say, how much Greenland is contributing to global sea level rise, which is still, rather small. It's only about 3 millimeters per year of sea level rise right now is a global sea level rise. And Greenland probably contributes about, 0.5 millimeters to that sea level rise. But this is one of the big uncertainties right now when we're thinking about future climate, is how are these ice sheets going to respond, and how are these glaciers going to respond as the planet continues to warm. Of course, glacier fluctuations are also really good, clear indications of climate change because they respond very quickly to changes in temperature. And at NSIDC, we have quite a bit of a glacier archive of photos. So this is the McCall Glacier in the National Wildlife Refuge, taken in 1958. This is the same picture taken in 2003, and you can see there's been quite a retreat in this glacier in its aerial extent. Here's another example of Muir Glacier in Alaska in 1941, and then here is it in 2004. Quite a large retreat. And that's a part of the world that I actually have not spent any time in yet. I haven't been visiting the glaciers of Alaska, and that's something I would. This is just a time series from some colleagues over at INSTAR, which are just sort of across the parking lot from where I work, which is the Institute of Arctic and Alpine Research. And so they do a lot of glacier monitoring. And this is some mass balances of a few Arctic glaciers, which is basically showing that, back here when I started the measurements of some of these glaciers, through about 1990, it was pretty variable. It was up and down. Some years you'd have an increase in the mass balance, some years a decrease. But basically since the 1990s, there's been a more consistent decrease and just less variability. The trend is pretty much just going down for most of these Arctic glaciers now. So that's a change that we've been seeing in the last couple decades. Another important component of Arctic climate change is the permafrost degradation. So this is a map of permafrost for the northern hemisphere. So the well, this, I guess you call it fuchsia color, are areas that are permanently frozen ground. This lighter purple is areas of seasonally frozen ground, and then these brown or sort of colors, orange colors, are sort of intermittent areas of frozen ground. But permafrost occupies about 24% of the northern hemisphere, and of course they occur mostly in the Arctic region, but they can also go as far south as 26 degrees north, such as in the Himalayas and the Tibetan Plateau. Now there have been a lot of measurements looking at changes in permafrost temperatures. This is actually 20 meters deep, so you're pretty deep, and the temperatures are still quite below freezing. But these records begin in late 1970s here, and these are all just different sites in Alaska, but they're all pretty much showing the same sort of signal, an increase of warming in the lower levels of the soil at 20 meters deep. These are some soil temperatures more in the active layer, so the upper permafrost that tend to thaw in the summertime and then freeze in the winter. And this is from some Russian stations, and so you're seeing, negative temperatures here early in the record, and then all of these different depths that they've been monitoring have all been increasing over time as well. If we look just in general, in Alaska we see about a 4 to 6 degrees Celsius rise in the permafrost temperatures over the whole 20th century, but if we just look at the last 30 years or so, it's about 2 to 3 degrees Celsius, so it's definitely accelerated in recent years. Similarly, in Siberia, you see about a 3 degrees Celsius increase in permafrost temperatures, and same in the Canadian Arctic. In the Tibetan Plateau, the increases are a bit smaller, but they're also increasing as well. And, why is this important? Well, it's important not just because there's a lot of infrastructure impacts, which these are some photos of some infrastructure impacts. In Alaska, in Russia, also here in China. And I was actually reading, there was a presentation last week that the Arctic Council put on, and I was looking at some of the presentations that they were doing, and I found out that Alaska is right now spending more than $10 million annually to deal with issues related to permafrost thawing. So trying to repair the roads, trying to repair buildings, they're trying to move entire villages that are falling apart. So it's definitely having a huge impact on people's lives. The other issue with permafrost is that it contains, and the estimates right now are about 1,600 gigatons of carbon. So when the permafrost thaws and all that dead plants and animals start to become active through bacteria interacting with it, the potential for the methane release is quite large in the permafrost, because right now the carbon in the permafrost is more than double what's in the atmosphere right now. So this is one of the reasons that people are very concerned about warming in the Arctic in terms of how it's going to impact not just the infrastructure, but also how it's going to be impacting additional warming that will occur as the permafrost is released. Some other work that a colleague of mine, Katie Walker, has been doing is looking at the methane being released from lakes. So again, here you have the permafrost that's thawing on the edges of the lakes, you have permafrost that's thawing from below the lakes, and so you get these methane gases that bubble up through the lakes. And so this is an example of them still trapped in the lake. Here's actually a lake bubbling. I mean, it looks like it's boiling water as the methane bubbles up. And so work that Katie Walker's been doing, she's been trying to set up monitoring systems in the Arctic to look at the methane release. And just because it's been warming in the Arctic, you have more lakes, about 14% more lakes than you did 30 years ago. But you also have about 60% more methane being released from these lakes than it used to be, just because a lot of the permafrost around the lakes and below the lakes has been thawing, releasing all this trapped methane. And I was just reading her presentation too, because she was one of the talks, and they're actually looking in Alaska at maybe a way to start harnessing some of that energy, and maybe they could use it. I think some people in Holland have been doing that, so you can actually use it maybe as an energy source instead of letting it go just out into the atmosphere. There's also work showing that the Arctic is getting greener, so the tree line is moving further north. Basically, these bright green areas are areas where you have significant positive trends in the vegetation that's going on in the Arctic. And this is based on some data from 1982 to 2005. There are some regions where you have significant negative trends. I think over Alaska and Canada, a lot of that has to do with more forest fires as well as a pine beetle kill, which is affecting a lot of the forests. So some of these forests are now becoming carbon sources rather than, carbon sinks rather than sources. This in the boreal forest, I'm not exactly sure here in Russia what that is. I think it's a die-off in part of some of the trees because of the permafrost thawing, because they have trees in that region that are very dependent on the permafrost. And so as it dries out, those trees die and then get replaced by more pine type trees. The area that I've been working on in the last several years is looking at changes in Arctic sea ice, which in a lot of ways has become our poster child for climate change. Just to be clear, sea ice is frozen ocean water. Basically, it originates within the ocean. It does not include land ice, so not glaciers or ice sheets. It does not include any floating ice, so ice shelves or icebergs. So if the sea ice melts, it does not raise sea level, and that is something that's important to remember. And this is just an example of some images of what sea ice looks like. It comes in many different shapes. When it's first forming, it'll form sort of a brackish ice, and then these platelets will come together and they form what we call pancake ice. This is ice that's maybe a couple years old, so it's broken up into more sort of ice flows. You can get heavily rigid ice as the ice moves by the ocean currents. It piles up against each other, creates some huge pressure ridges. But just to be clear, sea ice is not icebergs. And this is something that it's interesting because I don't know how many times I've read a news report or a media report where we're talking about changes in sea ice, but then they show a picture of icebergs. And they're not the same thing. And it confuses a lot of people, I think, because, and obviously, I think icebergs are prettier to look at maybe than sea ice, but they're not the same thing. So when we're talking about melting of the Arctic Ocean, we're talking about not the icebergs, but the actual ocean that's covered by sea ice. So just a little background on sea ice in the Arctic. It has quite a bit of variability, seasonal variability. So in the wintertime, so here you have Greenland, Alaska, and Siberia. This is basically the typical extent of a sea ice cover during winter. It'll extend all the way down here to the Gulf of St. Lawrence. We got the Bering Sea and the Chukchi and the Sea of Okhotsk region. So it's about, I always forget to put this in terms of million square miles, so it's like 5 or 6 million square miles. I'm so used to working in square kilometers. So, and then in the summertime, it melts back quite a bit, and it pretty much is just then restrained to sort of the Arctic basin. And it then drops to about 3 million square miles. So that's basically, typically what you get every year. And when we talk about sea ice melting and disappearing, we're really not, this part we still expect to see every winter. Temperatures are still going to get cold enough for a long time for the winter ice cover to form. What we're worried about is what's happening to the summer ice cover, because that's where we're starting to see some pretty big changes. But if we just look at it in sort of an annual sort of time series of what's been happening to the overall spatial coverage of Arctic sea ice extent in the Northern Hemisphere, and here I'm starting in 1953, so even though the satellite data record pretty much starts here in the late 1970s, this is some earlier data from ship reports and aircrafts and submarines that give us an idea, a little bit of what ice used to be like before we had the satellites up in space. But you basically see that there's been, it's kind of stable for about the first 20 years of this record, and then there's been this period of decline that we've been in the last 30, 40 years. And on an annual basis, the sea ice in the Arctic Ocean is declining at a rate of about 4.3% per decade. But like I said, there's not a whole lot happening with the winter ice cover. What we're really looking at is changes in the summer sea ice cover. So this is the time series during the satellite records, starting in 1979, of the September sea ice cover, because typically that's when we reach the minimum amount of sea ice before the sun sets in the Arctic and it gets dark and cold again and the ice reforms. And so what we find is that, earlier in the data record, this pink line is sort of average, where we expect the ice to be in September. But as you go through time, we're starting to see these large pullbacks of the ice cover from that pink line. And more of the Arctic Ocean is becoming exposed to sunlight than it used to. Now in 2007, we had, it was quite a bit of a surprise for a lot of us studying the Arctic sea ice, because we had this drastic reduction. I mean, if you look at the time series here of September sea ice extent, and you get to 2007, you see a large drop. And there was a 26% drop between the previous year and 2006. So this white area shows you where the ice was in September 2007. The green line shows you where the ice was during the last lowest that it was recorded, which was in 2005. And then the pink and orange lines are sort of average. And what was interesting about this is that in past years, you might, if you had a low sea ice year in the summer, it would maybe be on the Alaska side or be on the Siberian side. It would sort of switch back and forth. And basically since 2002, it's been kind of going on both sides. And then in 2007, it got a lot closer towards the North Pole. And this is something that took a lot of scientists by surprise. It wasn't something they expected to see happen that summer. And there was a lot of media attention about it too, because it was sort of, people were grabbing onto this. Well, is this the end of the Arctic sea ice? Is it all going to go away now? One thing we don't know, of course, we wondered, well, what caused that large drop in 2007? And part of it was that there was a pretty unusual circulation pattern that set up that summer that promoted very warm temperatures and very strong winds. And I'm going to give an example of that by showing the sea level pressure pattern from June and July of 2007. So these areas in red are high sea level pressure. These areas in the purples and blues are low sea level pressure. So what you had was a very high sea level pressure developed here in the Beaufort and the Chukchi Seas. This is Greenland, this is Alaska, this is Siberia. And typically under a high pressure you have more clear skies, so you have less clouds. So one thing that happened was that you had more of the sun's energy could reach the surface and help melt away the ice. But you also had a very strong pressure gradient between the low pressure and the high pressure, which then brings winds in from the south. And so if we look at temperature anomalies, we'll find that in that region where you have a strong pressure gradient, so this is here the Bering Strait, Alaska, and Siberia, you had very warm temperatures, 4 degrees warmer than normal that summer, that helped melt the ice in that region. And you also had very strong winds that helped push the ice away from the coasts of Eurasia and Alaska towards the pole. So both of these things acted together to sort of take away all that ice. But while it was unusual, it wasn't unprecedented. So there's been other times in the sea ice record where you've had a similar circulation pattern set up, but you didn't lose so much ice. So the one thing we've noticed is that a big part of it has been that the ice has just gotten a lot thinner over time. These are estimates of ice thickness from a satellite that was launched in 2003 that provided us data for about 5 years on thickness for the Arctic Ocean, which is something that we really don't have a good feeling on, a good handle on. But it shows that a lot of the Arctic Ocean was rather thin, about 1 meter thick, really, really thick ice. So 8 meters thick ice was here north of Greenland and the Canadian archipelago. But the large parts of the Arctic Ocean were about 1 meter thick or so, 1.5 meters. So that ice was just more prone to melting out under this atmospheric forcing. Now, if we looked at the next springtime, so February, March of 2008, of course, after losing so much ice in 2007, a lot of that ice was younger, first-year ice that just formed over that winter, so it was much thinner than it was even the year before. So we may have thought, well, we'll have a new record low again in 2008 because the ice is even thinner now than it was the year before. But actually that didn't happen. So here's 2007, here's 2008. 2008 ended up a little bit above that in 2007. And then 2009 was a little bit closer again to sort of the trend line, which is at about 12% per decade decline in the Arctic sea ice in September. And then 2010 again was a bit below. But what this shows is that even though thin ice is important, atmospheric variability still plays a really large role in defining the ice cover every year. So while I can say with some confidence that this summer we're going to probably have less sea ice in the Arctic Ocean than we did back in the 70s and the 80s, I can't say with any confidence that it's going to be less than 2010 or more than 2010 because a lot of it depends on what's going to happen this summer, and we're not able to predict what the weather patterns are going to be this summer in order to say, well, are we going to have a new record low or not in the sea ice cover. And part of it is that has been a problem, I think, with monitoring sea ice, especially when we talk about it with media people, is that we don't have a good feeling on changes in ice thickness. Because if you're thinking about the ice extent is shrinking of the Arctic sea ice, well, what if it's just all compacting and it's just getting moved around and there's still just the same amount of ice there that's always been there? It's just that it's not as extensive. So one thing we've been able to do with satellite data is track basically changes in how old the ice is, which gives us an indication basically as how thick it is. Because the older the ice is, the longer it's been in the Arctic, the thicker it tends to be. So by doing that, we can look at changes in the thickness distribution. Well, these red colors are ice that's at least 5 years or older. This dark blue is ice that's 1 year old, so it first just formed over 1 year season. And you can see if you look over time, there's been quite a big change in the amount of the old ice in the Arctic basin. So this change is really significant in that if you have an Arctic that's covered by more and more of this first year ice, which only grows to about 1.5 meters thick typically every year, you're more prone to melting that ice out in the summertime, no matter what the atmospheric circulation patterns do. You're likely to melt it out. And right now, there is very, very little old ice left. This is from going through 2010. I don't have a graph from 2011, but at the end of last spring, we had only 320,000 square kilometers of ice that was at least 5 years or older, and this is the map of where that was. So just here, north of Greenland and the Canadian archipelago and kind of extending up here in the Beaufort Sea. Whereas back in the 1980s, you had more than 2 million square kilometers of this old, thick ice. And this is a key to, I think, what we're seeing in terms of the Arctic changes that we're seeing in the ocean, is that the ice is just transitioning towards an ice cover that's mostly first-year ice, which is a lot thinner. And just an example of what happened at the end of last summer, even though you didn't have a new, I guess, record low in the overall extent, if you look at the distribution of the oldest ice, you had the least amount that we've ever seen, and that's, of course, been true then extending into this winter. So where now you have about 15% of the ice is 2 years or older, back in the 1980s, it was more than half of it was that age. Another thing that's happening, of course, is that all the Arctic sea routes are starting to open up. In 2007, and every year since then, the Northwest Passage has been open. It's been navigable by ships. So you've got the deeper Parry Channel that's open. You've also had Amundsen's route, which would go this way, has also been opening up. You've also had the Northern Sea Route opening. So this is in 2008, and every year since then, this part of the Arctic is also opened up. And last year they had 2 sailboats, one from Norway and one from Russia, that left and went all the way around the entire Arctic, went through both passages. I think that was the first time that they tried to go all the way around. I think the Russians won. It was a little bit of a competition as to who would get through fastest. I think the Russians actually got through quicker than the Norwegians, but this is something that's, of course, of interest to a lot of people, because you're opening up these trade routes now that used to be, almost covered with ice. Of course, the natural thing is, what's going to happen in the future? Well, one thing that we know from our climate models is that if we continue business as usual, so if we allow the emissions of greenhouse gases to continue to increase in our atmosphere, all of our climate models say that the ice cover in September is going to go away. We're going to lose the summer ice cover. They vary quite a bit as to when that date's going to be. Some of them say it's early as 2050. Some of them say it's way beyond 2100. But every one of them shows the ice going around away. And the black line is just the average of all of these climate models. And the dotted black line is 1 standard deviation from those models. What is interesting, if you then plot the observations on top of it, you find that it's actually going away faster than our climate models have been telling us it would. And that certainly has been, somewhat of a revelation. I was giving a talk several years ago and just sort of extrapolated based on what the data's been doing, what I thought the time period would be for when we would see ice-free conditions in summer. And I was asked, well, how does that compare with the climate models, which I thought would be pretty aggressive, but actually turned out that the observations are showing this decline much, much quicker. I think this graph is important for a couple of reasons. One, in that all of these climate models would be in their own phase of natural climate variability, so they could be showing increases or decreases, depending on what their internal variability is doing. But the fact that they all show a decline, which is at least in qualitative agreement with the observations, suggests that greenhouse gases are playing a role in these models in defining that decline that we're seeing in the Arctic sea ice. But if you look at this, after 2007, there was a lot of speculation that we might have been passing a tipping point, but then we did see some recovery following that. So it also shows, if you look at these models, though, there's a lot of variability. And We could expect it to go up again for a while, but as we go out into the future, we're likely expecting to see the Arctic Ocean opening up in summers. The one thing that's interesting in climate models is that a lot of them suggest that you could have a very rapid transition in the phase between having an Arctic Ocean covered by sea ice to one that's nearly completely ice-free. And when we saw the thing that happened in 2007 where we had a 1.6 million square kilometer drop in just 1 year, that was pretty comparable to what we see in the climate models. And we thought, there's a lot of speculation that 2007 was sort of this tipping point, that we're going to have no return in the sea ice. But there isn't really a definitive tipping point that you can say that it's going to happen and then all the ice is going to melt away. The one thing that does seem clear is that you need to have the ice thin in order for these rapid changes in the ice cover to occur. So if we look at the climate models, they show thicknesses that are on average, about the same as what we're seeing in the observation data right now. And in the climate model, in this climate model, what causes this big, large reduction is actually changes in oceanic heat flux convergence. So bringing warm water into the Arctic is what causes this big drop. But it only happens when you get the ice at least to a point where it is thin enough where it could be that vulnerable. But I think what we're finding, just even if you look at the last few years, is that there's still a lot of variability in the climate system. And just because you're on this downward trend towards less sea ice, it doesn't mean that there's going to not be ups and downs along that curve. You're going to see quite a bit of fluctuations. So you don't necessarily think that a tipping point or like a critical thickness you're going to get to where you're going to lose all the ice. But it does seem clear that you need to have thin ice in order for it to go. Now, of course, as we lose the ice in the Arctic, we're going to see increased access in the Arctic because these shipping routes are of a lot of interest to a lot of people. And a lot of groups right now are trying to meet and trying to figure out sort of who owns what part of the Arctic. Russia says they own pretty much everything from their coast to basically the center Arctic because that's where their continental shelf extends out. I know the Canadians, they're concerned about their access. The U.S. hasn't really been doing a whole lot about our access in the Arctic. But I think that's going to be changing because I was reading that Obama was very interested right now in developing a national policy about how to do governance in the Arctic. Here's an image of just today's Arctic marine use. So where the regions are where we're seeing a lot of ship activities. So the blue areas are where we're doing mining right now. So we have nickel and copper over here on the Russian side, Eurasian side, zinc and coal up here by the Bering Strait, and also some high-grade iron ore in Baffin Bay, the Canada region. This is where we've been seeing a lot of tourism. So Greenland has a lot of cruise ships that go around it, as well as Iceland. So there's a lot of cruise ships in this region. In Svalbard, of course, off the coast of Norway. There's even been ships trying to get to the North Pole, so icebreakers bringing people. The Bering Strait and the Northwest Passage, of course, also see quite a bit of tourism. Here are also the regions of major fisheries. So you've got the Bering Sea, the Barents Sea, and Iceland are regions of a lot of fishing activity. These are all the current oil and gas activity that's going on in the Arctic. So there's also, of course, ships related to transport of the oil, especially on the Russian side. There's a lot of transport that goes through in this region related to oil and gas. There's also a lot of Navy operations in the Northwest Passage with the Canadians, and also Russians have been doing quite a bit of work on their side as well. And then there's all the boats out there for science support as well. We've got the U.S. Coast Guard Healy operates mostly in the Beaufort and the Chukchi Seas. You've got icebreakers that go up through the North Pole area. So there's a lot of shipping activity in the Arctic. In 2004, there were about 5,500 ships. I was trying to find a number for 2010, and I couldn't find anything online, but this activity is increasing quite a bit. I know last year from this meeting I was at for Homeland Security up in Fairbanks last fall that the number of ships that go into the Northwest Passage had doubled from the year before. So there's a lot of activity now in the Arctic Ocean. And we can expect that to increase as the ice continues to retreat. Of course, there's a lot of interest in the Arctic Ocean as well because of all the oil and gas that the USGS believes to be there. And so these are maps of the oil distributions and the gas distributions. So this dark green is more than 10 billion barrels of oil, and the red is greater than 1,000 cubic feet of natural gas. Of course, the Alaska side has quite a bit. Russia does as well, especially with the natural gas resources. But basically, they estimate about 90 barrels of oil in the Arctic and about 1,700 trillion cubic feet of natural gas. And then there's also about 44 billion barrels of natural gas liquids. So most of that is occurring in the ocean, of course. So as the ice is retreating, a lot of these groups are interested in accessing oil and gas. And a lot of oil companies have already made claims in certain parts of the Arctic Ocean to start doing their drilling once they get a chance to do that. But of course, the Arctic is also home to a lot of species as well as people. And so any of these climate changes that we're talking about are certainly going to impact the species that exist in the Arctic. And the ones that especially rely on the sea ice, like the polar bears and the seals, for their livelihood. I mean, without the sea ice, it's hard to imagine that these species will be able to survive because their whole life depends on the ice. Species like the muskox have been affected a lot recently by just the fact that there's been more freezing rain falling on the ground, causing ice to form on the surface so they can't actually reach the vegetation to eat it during winter. That's been a problem for some of the muskox. Ivory gulls also are connected strongly to the ice, where they give birth to their chicks really close to the ice, so changes in the ice cover affect them as well. And the polar bear is an interesting thing because it really is kind of hard to imagine that they can survive if we go to an ice-free summer in the Arctic, because they really need the ice as a platform for hunting seals, which is their primary food source. And for every week that it is not hunting, it loses 22 pounds. And this has been really impacting the ability of the female polar bears to reproduce, because they just don't have the fat stores to reproduce. And I know in the Hudson Bay, where there's been pretty large changes in the ice cover, they've been seeing a really negative impact on the polar bears in that region. And I can imagine the Beaufort Sea is having the same problems, because a lot of those bears, that's where the ice has been retreating a lot in recent years. And so they're stuck on shore for longer periods of time and able to get to their food source. But you also think that the whole ecosystem that they depend on is also depending on that ice. So the krill that forms and the plankton and the shrimp that form underneath the ice, which then feed the fish, then feed the seals, and then feed the polar bears, all of these are going to be impacted as you change the seasonality of the ice cover in the Arctic Ocean. Seals are also feeling impact, especially the last couple of years. The Gulf of St. Lawrence typically has ice in the wintertime, but these last 2 winters the ice did not form. There was very, very little ice along the edges. And from Environment Canada, they reported that on the first day of spring in 2010, they only found 600 seals in the Gulf, compared to typically 30,000 they normally see. So it's been having a big impact on the seal population in this region. And Humane Society International right now is having me do some work for them looking at future projections of the ice in the Gulf of St. Lawrence, because I think they want to try to stop the hunt, because Canada still hunts the seals in this region. And since these seals are suffering right now from the lack of sea ice forming in the wintertime, they're trying to actually reduce the hunt on the seal population in that region. It's also important to remember that a lot of people live in the Arctic. It's very different than the Antarctic in that there's a lot of Inuit and Nup'iot communities that depend on the sea ice, not only to travel and access their food, but it's also their whole basis for the cultural identity. And so if we change the ice cover, it affects their access to their food sources. It's also, if you're warming up the Arctic, it's also affecting the way that they do things like food storage. They used to just bury things in the ground, and now the ground is warming, so now they have to get refrigerators. A lot of them use frozen rivers as a transport system, and now that the rivers aren't freezing over as much, they also lose their ability to get around in the Arctic as well. The people in the Arctic are really, they're very concerned with climate change, and I know that they've been pretty big advocates for trying to get some changes going on in their communities. They had one representative that was suing the United States government based on climate change, because she felt like we were responsible for a lot of the changes that are happening in the Arctic because of our emissions. But it's also hard for the local communities in some ways, because they're dealing with a lot of their own problems, a lot of domestic violence problems are in a lot of these native communities, and alcoholism. So it's been hard for them to get around as a group to really do much about climate change. But certainly their whole way of lives are being affected quite profoundly by the changes in the sea ice. And certainly with their ability to go out and hunt and go on the ice before, they used to be able to just use their traditional indicators for what the weather was going to be and what the ice conditions were going to be like. And they were able to go out and travel safely on the sea ice. But these indicators are changing, the ice conditions are changing, And they're not as confident anymore about their ability to predict what the ice conditions are like. And they're actually setting up a network system of communication in the Arctic so they can communicate with other hunters, let people know what the ice is like so they don't get stranded out there. Because there's been a lot of cases in recent years where hunters go out on the sea ice, the ice breaks up, and then they're trapped out there on the ice and needed to be rescued. And the one thing that I would say, in the Arctic right now, the U.S. has no infrastructure to support search and rescue missions. We only have one icebreaker that operates in the Arctic. We don't have any radio communication set up along the coastline, so we're not really prepared to deal with oil spills or to deal with search and rescue missions up in the Arctic right now. And so the Coast Guard's really trying to look at some solutions on what to do. A lot of these communities are also facing coastal erosion, in part because the permafrost is thawing, so the foundation is thawing, but also because as the sea ice retreats, it exposes these coastlines to storms and big waves. And so these big waves come, and combined with the fact that the permafrost is thawing, entire communities are having to be moved, actually, because they're being threatened. Right now, they have about 280 communities that are threatened by coastal erosion. 6 of them right now are in jeopardy of falling completely off the ocean, and so the entire towns are needing to be moved. So this is a big problem in the Arctic right now as well. But in terms of the rest of us, I mean, if we think about melting back the snow and melting back the sea ice, we're losing this really reflective white cover that helps keep our planet cool and helps control all of our circulation patterns and all of our weather patterns that we see. So if we go and we remove this ice, which reflects about 85% of the incoming solar radiation, and it's covered by snow, and we expose ocean, which only reflects about 7%, so it absorbs about 93% of the incoming solar radiation. You're basically going from a surface type with the highest reflectance to the least reflectance. And this is going to warm it up even more. And in fact, we're already seeing that temperatures are warming quite a bit in the Arctic. This is looking at just autumn temperature anomalies, so just air temperatures. And they're focused mostly over the Arctic Ocean, where you've been losing the ice. But atmospheric circulation can spread that warming out over land. And so even though you might have 5 degrees Celsius warmer temperatures where you've been losing the ice, that warming gets spread out over the land areas as well. And if we look at how this will impact land temperatures, these have been some simulations from models looking at periods of rapid ice loss versus periods of no or moderate sea ice loss. These temperature projections are much higher if you have these periods of rapid ice loss, if you're just removing all of that ice and you're warming up the air above it. And this is what people are concerned about, because the carbon content of the permafrost is more than double what's in the atmosphere. And so this is a huge potential feedback that we are looking at in terms of how it's going to impact our climate. And this is just an example of, basically, if you don't do any carbon feedback effect, you would actually see the Arctic becoming a carbon sink over time, because you're going to have more trees coming, the Arctic's getting warmer, you have more trees, you're going to take up more carbon from the atmosphere. But if you get the feedback from the permafrost, it actually becomes a net carbon source in the Arctic. And this is something that a lot of our climate models were not taking into account, and the next generation of the climate models will be considering this impact. One thing that you probably noticed at least the last couple winters is that there's been these cold outbreaks of temperature from the Arctic into the lower latitudes. So back in 2010 and 2011, this past winter, we've had very cold temperatures and we've had a lot more snow cover. In some ways, this can be related to changes in the Arctic because of the sea ice loss, because you have this warming in the autumn. You're pushing up, it's like kind of like a bowl shape. You're pushing up the pressure level, pressure patterns up. And so it causes the cold air to spill out of the Arctic into the lower latitudes, which then, of course, can also impact not only on the temperatures, but precipitation. And so it's interesting that even though we expect snow cover to decline in the future, the winter snow cover seems to be going up, and it's mostly driven by increases over Siberia right now, but they're getting a lot more snowfall as the sea ice has been retreating in summer. So, can we expect harsher winters? I think it's too soon to say, because a lot of this is based on just a few years of data where we have some big changes going on. But this is something that climate models do suggest will happen, is that we're going to have harsher winters as a result of a warmer Arctic, which seems sort of counterintuitive, but It does make sense in some ways in that you're really changing the circulation pattern up in the Arctic, and that's going to spill out into where we live as well. So just some final statements. We are aware that a lot of components of the Arctic environment are undergoing rather large changes right now, and it's definitely having an impact on a lot of people and wildlife. All of the changes that we're seeing in the Arctic are consistent with climate model simulations. Using the observed record of greenhouse gases, when you run those models without putting the observed record in, you don't get these changes that we're seeing. So it definitely seems to be a large part related to greenhouse gases in the climate models. The sea ice loss, though, is outpacing a lot of our projections, and so it's been sort of speculative as to when we might see an Arctic Ocean that might be ice-free. I sort of believe it might be around the mid-century. There's some colleagues of mine who say it might happen as early as 2016. I think that's a bit aggressive, but he thinks that the ocean is actually melting a lot more of the ice from below than we've been giving it credit for. I guess we'll have to wait and see. But it's already having a large environmental impact in the Arctic, not just on species and the people, but also on weather patterns that are starting to affect the rest of us as well.